If you could you please give me a green check? Thank you, friends. Go ahead, please, and give me a green check if you can hear me. And seems it is up and running here. Need to be back. Okay, great. All right. Tonight, my friends, we're going to go over level 21. And number 21 talks about measuring instruments. So we're going to spend some time, Juan, my friend, talking about measuring instruments. But before I start, you guys need your eye attention, so I don't want to see the exclamation mark right next to the name. So if you go to a different site, it will get me these exclamation marks. So keep an eye on that one. Okay. So two things. Few of you guys have been emailing me about the homework. And you can't download it and so forth. Here's what you get, and listen to me carefully. If you want me to email you all the homework, I should be able to do that. But do me a favor, drop me an email at ccurdy. I'm gonna write it right here. ccurdy. Curdy at Dunwoody of course the Dunwoody right, Chad. You think you the guys, don't you? Alright. So Dunwoody .edu. So do remember, guys, if you .edu. If you need to email you all the homework, can you guys one more time? Can you all hear me? Can you all hear me? You can hear me? Could you please give me a green check if you can hear me? One more time, check if you can hear me. Okay, great. So do me a favor, drop me an email on ccurdy@dunwoody.edu if you want me to email the homework to you, so you can do it. This is, guys, our three more classes, then we're done. So we're closing. We're getting to the end here. And if you submitted your homework, please do so. If you want to download it from the network, no problem. Just email me, and I will be able to email you all the homework that you need. But drop me an email at ccurdy.dunwoody, and I should be able. My email is right open. If you guys drop me an email, I should be able to see it. Okay. Any question about the homework, guys? Because I've been getting emails about the homework and chats. Any question about the homework? Any homework? What I do the homework, guys, I collect them at the moment, and I can, if you want the answers, I can email you the answers and so forth. But at the moment, I'm collecting them. So, a question about the homework, guys? I see that chat here. From night instead of stream money able to be okay. Were you guys? The question is, were you guys able to download it from the site? How many are able to download the homework from the site? Check yes, X no. How many were able to find the site and download it? A few of you. No problem. If you were not able to find them, just email me at this moment, and I should be able to forward them. Okay. Okay, you know which assignment we have not done. Just me an email, guys, and I will email you the ones that you have done. Just why don't you guys go ahead and drop me an email, and I will send you all the assignments, and then which one you did because you have them. If you don't have them, I will tell you what I received from you. I also can send you an email, individual email, what I have received from you. So, any more questions, guys, about the email, the homework? I know I brought this to the last minute, guys, and I know it's confusing. So just do your best on it and submit it. That's all what I'm asking for. What part of the plan deep plan to start with, but just do your best on it and submit. One more. Any question you have about the homework? Do me a favor, just drop me an email when you have a chance. Okay. If you remember last week, we did parallel series circuit, and we talked about Thevenin and Norton and superposition. And these are methods of analyzing the circuits, and Kirchhoff's laws, and a lot of analyzing the circuit. Thanks God, I'll go ahead and get my email out. Now moving on to something more tangible, more measurable, which is measuring instruments. For other guys, electrical contractor who used to say a good electrician is as good as their tools, and part of tools is your meters. So if you're doing maintenance, which I'm sure a lot of you, how many of you guys do maintenance on a daily basis? Maintenance, how many of you do maintenance? Green chest, no maintenance. How many of you guys like your main job is doing maintenance? Your main job. Okay. If your maintenance or your main job is doing maintenance, don't. But if you're doing maintenance, guys, tools and measurements and knowing how to measure the voltage, the amps, the watts, the impedance, the reactance, the frequency, all these parameters is a must. If we're shooting a motor and you need to find if the winding is shorted, you need to be able to make the voltage, make that winding. So these are very, very important, guys, the measurement instrument. I'm going to convince you how important it is, especially if you're doing high-profile maintenance on motors and generators and switches and lights and so forth. But before we do this, as we have done in the past, if you guys don't mind, I'll go ahead and start with the quiz that we did last week. So with last week's quiz, my friends, I looked at it seems everybody did a great job on it. I'm going to go, that's why I'm going to go quick. But before I go, I'll ask you, my friends, does anybody have any question in particular about the quiz? A question in particular that you want me to give attention to? Any questions? I know there's a few questions at the end calculation, so I'll try to see how much I can do, guys, without spending the whole night doing calculation. So, any questions about the quiz in particular? Feel free, guys, if you remember as we go through. Okay. Talk about in series circuit. Our answer for this one is B. The sum of the voltage drops of the individual resistance must equal applied voltage. Voltage across any circuit branch is the same as the total voltage. That's a parallel circuit, so that's no. The current is the sum of the current in a series circuit. That's no. That's a parallel circuit. The total resistance is equal to the reciprocal. Absolutely not. So now is B. Input circuit. Our answer for this one is A. The total current is the sum of the current that goes through every branch. B is wrong because the current is the same. No, the current changes. The total impedance is the sum of all the impedances of the resistance. That's no. The voltage drop adds up. No, it doesn't add up. It's equal. Okay, so these are straightforward. Three statements. The algebraic sum of the currents entering and leaving a point must equal 0 is an expression of number 3 is A, which is Kirchhoff's current law, not the Thevenin, not the Norton, and not the superposition. And I don't know about you, Joe, my friend, but that you can summarize a complete national grid into a resistor and a voltage source. And if you guys remember, it says you can summarize a whole national grid or a whole power system in your plant into a resistor and a current source in series. And for position, say if you have two sources of power, you can get a current 1 from source 1 and current 2 from source 2 to get the total current, add them up algebraically, meaning if they're going in the same direction, you can add them up, right? And if they're going in the opposite direction, subtract. Going in the opposite direction, you subtract them. So that's basically the three very important series that we did. Number 4. Number 4, my friends, is the current in a branch circuit in a branch of a circuit supplied by a multi-power source can be determined by finding the current produced in the particular branch by each of the individual source acting alone. Each source must be replaced by a resistor to the internal resistance of the source. The total current flow through which will be the algebraic sum of the individual produced by each of the power sources. This is a statement. You guys remember number 4. This is a statement of superposition. You remember superposition is you can do analysis based on source number 1 and then resistor for source number 2, and you do the same thing for source number 2, resistor for source number 1, and you add them algebraically. Always to reduce the circuit network into a single current source and a single resistance in parallel, in this case, the Norton, right? So 5 is our answer for 5 is C. I'm going to these guys because they're easy. The statement, the algebraic sum of the voltage sources and voltage drop is must equal to 0. That, as we all know, is number 6. 6 is A. Kirchhoff's voltage law, not the current law. Now, to simplify a circuit network into an equivalent circuit contains a single voltage source and a series resistor. And if you guys remember, the Thevenin is voltage in series, and Norton voltage in parallel, current in parallel. So always you remember it this way. And the other one would be a current source actually in parallel with a resistor. Yes, anybody has any question about these? Any questions, my friends? Okay, number 8 says resistor of these amounts connected in series for one branch of parallel circuit, and resistors these form another branch. The total resistor of the circuit is, so very interesting. I have 2 resistors. I don't know if you guys visualize what they're trying to say here. 2 resistors. I have resistor 325 here and 275 here, and the resistor here, 2 resistors. This will be the 150 and 50, 150, 250. I want you to find the total resistor. What happens if you go cut all these and put one big fat resistor here to list all of them? As you guys know, if you add them up, so that 300, this will be what is it? 5. Let's look at the 3 plus 3. This will be 600, right? This will be a 600 here. And if you take 300, 300, 400, this will be a 400. 400, 300, just add them up. And then take the sum there, the series 1 and the parallel 1, multiply them and divide them by their sum. Divide them by their sum. And if you do this, divide them by their sum, you will get our answer, which is A, D, which is D. Just by looking at it, guys, looking at it, actually you don't have to do the math. By looking at it, you know that it shouldn't be 1,000 because just by looking 600 and 400. When you add 600, I know 1,000 is impossible. I know also 600 is impossible because the total resistance must be smaller than the smallest. And I know it's 400 also impossible because the total resistor must be the smallest. So actually you don't need to do the work. You could have just looked at it and see the smallest, the 3 of them are not right. So method of elimination, you with the 4. Any comments, guys? Any comments about this one without doing the math? Okay, moving on, my friends, into Ohm's law for the calculation. If the circuit in question number 8 carries 2 amps of the current, the applied voltage is, so the circuit carries 2 amps. Okay, question number 8. Let's go back to question number 8. If it carries 2 amps, okay, and voltage is, you have a 2 amps, guys. You multiply it by what was the voltage, the 240, multiply by 240, right? to a healthy 480. So 9 and 480. Any questions about this? So they're saying, hey, by the way, here's the total resistor and source. What is the source voltage? What source voltage? If we discover there's a 2 amps sneaking through the wire, and the total resistor is already found as 240. It's okay. You multiply current by the voltage, they'll give you a total voltage. Comments? Any questions about this? Any questions? If question number 8 carries 2 amps of the current, is carried through the first parallel branch, which has these 2 resistors. So you know, guys, what current goes through the first branch. You know, if you go back here, we need to use the current that's going through let's say I1. Okay, the first branch. Can you guys see that? First branch. The first branch. So that will be easy because the voltage. You guys remember what the voltage was that we found it? 80. So if you take a 480 by the 300 by 600, and that gets you 10 as B, and B, right? So 480 divided by what was it? 600 equal B.8. Any question, guys, about this? Why? Because the voltage source. Here's my voltage source that I found, and here's expand resistor, guys. Right? This is my 325. And this is my 275. And they're asking me what is the voltage across both of them right in here. Oops. What's the voltage across both of them, which is right in here? What's the voltage if you measure with a voltmeter? What do you get? This is the same voltage, guys, as across here, right? That is the same voltage. The same voltage. Why 240? Because I made a mistake. It should be 480. Thank you. I divide by 480. Absolutely. It's 480. The volt we found, guys, is 480, which is this here. That's just a mistake. Typo. So 600 give you 4.8. One, guys, this is analyzing the circuit like we did. We have the next 5 questions for them. The total resistor is, and I wanted to get right away into maneuvering it. Just looking at these, I have 300. If you take these together, you add this to this, right? So 200. This is a 400, right? From the get-go. And if you take this and add it to this, this is 600, right? Here's my 600 and 300 from the get-go. And if you guys remember, we just have done that one. If you do math, and then if you don't remember, just do the 600 multiplied by 400, right? 400 divided by 600, 400, right? That should get you 240. That should give you 11, which is 240. Any questions, guys? Any comments about this? Any questions? Straightforward. Add the series, and then find the parallel. So that's basically question number 11. I will remind you guys that there's a 1 amp here. So let's keep going. Voltage is the applied voltage. If you guys remember, we found the resistor right in here. 240. Right? So we found the resistor 240, and the current is 1 amp. The current is 1 amp. So 12 is 8. If you 1 amp, then to find the voltage equal 1 times the total resistor, which is 240, and that gets you at 240. Any comments, guys, about this? Any comments about the total resistor, total voltage? I don't know, guys. If you remember, when you do the total voltage, as if the whole circuit here has been eliminated. Anything is eliminated, and your new circuit is this circuit here. This is new circuit. Everybody know that's what an equivalent circuit, or when you combined and the parallel, as if you got rid of all these circuits, all the resistors. Up to 13. I1 and I2. Here's my I1 and here's my I2. To find current I1 and I2, guys, the easiest way is to take the voltage, which is we found 240, right? Because the same voltage right here. 2, can you guys see that? And divide this by the total resistor, which has to be 600. I believe we did that one. 13 is B. 13 is B, which is 0.4. If you do that, you find 0.4. And I don't know about you, my friend Joe, the current going here and all the way in this branch is the same. So basically, the current I1 and I2 is actually 0.4. The current I1 and I2 is piece of cake, 0.4. The I3 and I4, so asking about I3 and I4, there are two ways, guys. If you guys remember, we've just found that the current entering here is 1 amp, right? And leaving this area here is 0.4. And what do you think the leftover? So I have 1 amp entering a point, leaving the point. So what do you think the current here is going to be? The leftover. So we take 1 minus 0.4. That will get you 0.6. 0.6. So it actually is 0.6. The thing in I3 and I4. Any questions, guys? Any questions? Any comments? Any? So this is the symbol analyzing the circuit step by step by thought. That's something like, you will see something like this similar on the final, definitely. Step, no complication, just so this one, the voltage drop through each of the 4 resistors is, so that's 15. Is this, I have the they're giving us the voltage drop across each one of these resistors. If you get the current, let me just tell you right in here from the get-go, I'm going to go and grab my, I already found my current, so I'll go grab my current, and I'm going to say the voltage is, it's going to be right here, 0.6 multiplied by 150, right? And here is 0.6 multiplied by 250, and up to 240. And then the voltage here is 0.4 multiplied by 325, and here should be 0.3 multiplied by this resistor, which is a 2 and a 7 and a 5. Let's do math on that one. So 15 should be D. You come up with these numbers. If not, either you made a mistake, I made a mistake, or you guys have invented new science. Any of this? Any questions? I hope asked on these. So definitely the last time probably we'll hear chat guys talking about these. Another figure, guys, this is a little bit more complicated. So answer the next 5 questions. The total resistor is, as you guys can see, we're going to add, I'm not going to do all of them, guys, but I'm going to tell you the method here. You're going to add these two together, and then you add, multiply these two together and divide them by their sum. Multiply these two together and the sum, that's the parallel, okay? Then, friends, then when you total these together, and you total these together, you add them up with these. So all stuff that I'm doing here is going to add up, and then give you 16 should see. So to it 600 times 900. I'm just going to do the parallel here. 600 times 600 divide by 900. 100 in this side, and on the other side 500, 750 by 750 plus 500, or 500 plus 750. 150 to it, and you had 140 and 250. So gimmicks, nothing. Any comments? Any questions about this? Any questions of finding a total resistor? Moving thing, the total circuit current. Let me just remind you guys that we've just found the total resistor number slot number 16 is C, 1200. So total circuit current, the total circuit current as if everything here has been replaced by 1200, right? 1200 ohms. So 120 by 1200, you divide 17, you're going to find an A. So the current is 0.1. If everything has been sized, the circuit has been changed into just one resistor, right? Comments? Any questions about the current? My friends, go into the current I1 as with I1 guys, and note it's the same as, right? It's in series, so the same as the series circuit. So number 18 is A. If you don't believe Chad, do you guys remember that the I1 is in series right here? If you expand it, it's going to stay the same. So I is 0.1. Okay, voltage drop E2 and E5, my friends. So then take the total resistor for this one, right? Total, and multiply them by the current, which is, so I'm to take the 500 multiply it by 7 and divide it by 500 plus 770. I have to keep moving guys here, and then multiply this. What was the current? The 0.1 multiplied by 0.1, and after you go 19, you should be able to find D from 19. So that's voltage across E2 and E2 and that's the voltage across E2, and voltage across E5, guys. You're going to take these two and do the same thing for them. Multiply these divided by their sum, multiply them by 0.1. That gives you E2 and E5. Any questions about this? Any question about finding the voltage? Finding the voltage? I would tell you a secret if I told you that when they ask about the voltage across these guys, it's as the voltage right here, right? So if you take the two resistors in parallel, these are the voltages that they're asking about. So for a resistor, all what you have to do is just multiply by the current with 0.1 because it's going through two of them at the same time. And I knew that the voltage across both E2 and E3 is the same. I7, the current I7, my friends, right in here. So here's the current. Look at that. That's a tricky one. The current came here, split, right? Split and came back, join ground, right? So this to this point is 0.1. When it split, I don't know. When it joined again, I know it has to be 0.1. Split again, I have no idea. I can find it if I want to. And join, it's 0.1, and it continue all the way to 0.1. Okay, so if the thing is about the current in I7 is going to be 0.1. So we did 0.1. Okay, any question, guys? Any question about any of these homework? Any about the homework? So that's straightforward, my friend Eric. No gimmicks, nothing. One. Okay, moving on, guys, into measurement instruments. To help me with the measurement instruments, guys, make sure you are into chapter 21. And by the way, we are on track right now. Chapter 21, guys, we have 3 more chapters to go until the end of the semester. It has been alright for all of us, but I hope it was a good one. So we're measuring instrument. To help me with the measuring instrument, please go to your slide, page 21.1. Spend some time talk about basically meters, the principle of working for meters, DC AC meters, multi-voltage meter, amp meter, ohm meter, watt meters. So that's kind of the name game tonight, if you guys don't mind. And so that's what we're going to be spending some good amount of time. And also, if you, my friends, have If you have the book, uh, Delmar electrical book, if you have this book, guys, go to chapter 9. Chapter 9 has really good explanation about the meters, about meters. So meters, as I said, guys, before, a good electrician if you know how to use the meters. For the most part, unless you guys in low voltage, for the part, a multimeter that can get you the voltage, amps, and the ohms. And a few here, I have a few of my own here. That's all what you need as an electrician. So we're going to go down to the basics and talk about voltmeters. And I hope everybody, when we say a voltmeter, it is measuring the volt. And we have an ammeter. I hope everybody knows that we are measuring the amps, the current. And we have an ohm meter. It's measuring the resistance. So this from Ohm's law. The single most important thing from Ohm's law, if you guys remember the E here, but this will give me I, right? And this will give me what? The R. This is Ohm's law. The single most important thing that we do is actually related to Ohm's law. And if you guys remember how we said, if we put the E and you measure R and multiply by the current that goes through it, it must equal the E. That is not surprisingly that the three most important meters are actually related to Ohm's law. Can you guys see that? I don't know if anybody noticed this. The three important meters that we use related to Ohm's law. And why? Because Ohm's law is the single most important thing, governs the science of electricity. So that's what we're going to be doing. We'll talk a little bit at the end with oscilloscope for those of you guys who do low voltage and power limit technician stuff. So that's basically what the name of the game is. But I emphasize how these are directly related to the Ohm's law, Instruments. Analog. Let me ask you, how many of you guys use analog meters? How many of you guys use analog, not used, use? How many of you use analog meters to get certain things? Analog meters like analog ammeter, analog voltmeter. Analog meters, they have their advantages, obviously, and disadvantages. More power people like us, I assume all of us are in the electrical power. They use easier, argue more accurate most of the time. So the analog meter, guys, it looks like something like this. This is a multimeter analog meter, and I want to bring your attention, guys, to the ohm, so you can use. You start from here 0 and go this way at the top. That will get you, and you set yourself at the ohm. That will get you all the way up to 1K here, and open. I don't know if you guys know, when you have short, closed is 0. If you reach 0 ohm meter, this means a closed circuit, short circuit basically. And if you leave an open, if I have, let me see how I'm gonna measure this one. Let's see it this way. I'm gonna go and measure. Here's my circuit. Here's my 1 volt, and here's my load. I don't know how I'm with that one. So if you guys go measure and the load, and let's go. Let's just open. It's just this one. I don't want the voltage here. There you go. And I'm going to go directly and open the switch. I open the switch, guys. I went and I grabbed my ohm meter, and I want to ohm this resistance. Of course, you have to open the switch. Okay, if your measurement is 0, if you measure 0, what would an indication if you measure 0? So I have a meter and I measure 0. And it would tell me what would that be an indication of? This is a load. This is What would that be, guys, if I measured 0? Anybody can tell me if the ohms 0? Anybody an idea what would that be? What would that be? Okay, but it's measured 0. Just saying it gives you continue, but I have 0 ohm. 0. Not 5, 10, 20. Thank you. I see the word. It's you have short circuit, Chad. You have complete short circuit between these two. So we're shunting it. That's the measure 0. Now, what happens if I measure, guys, a very high impedance? Very high. Anybody can tell me what happens if I measure a very high impedance? Would that be? What's an indication? Very high, huge impedance off the scale. And tell me I'm measuring right here, ohmmeter, and I'm measuring very high value. Anybody? You have a short circuit or open circuit, guys. So let's give it a shot. What would that be? Chad? Anybody? If you measure not complete, well, remember we're measuring right here, looking at the circuit from right in here. This circuit complete, right? I'm going this way. This should complete. If impedance, guys, you have an open one here. Let's just go get this. This is basically you're looking at an open circuit. You're looking at an open circuit. Open circuit will give you very, very high impedance. So that's basically a way of using the ohmmeter for resistive loads to make sure that you have a short circuit or an open circuit. Again, be very careful. Don't use it when it's hot. Don't use ohmmeter when it's in. So that's basically a few principles. The other one I want to mention, guys, look at this one. I have an AC, DC, different levels from 0, 50 to, so you can set yourself in more sensitive. You can boost your scale all the way up to 12 to get more sensitive measurement. Then you can go up to 60 and all the way up to 300 by adjusting your scale. There's voltage, I believe, and right underneath it, my friends, is your current. See current, and you can have the same scale here, as you can see, more sensitive to the less sensitive scale. So the analog meter, and I bring to your attention, guys, analog meter is not a whole lot used, I guess, unless certain applications. You have indicator. If you have not used some of this, it's like your speedometer, and you guys, that pointer will point to a certain area depending which scale are you. Are you measuring ohms? Are you measuring amps? Are you measuring voltages? If you're measuring amps, are you at the 30 scale? So if you're at 30 scale right in here, so you can measure this point based on the slide, so you get your measurement. So that's basically if this one goes directly, say, to here, just make it, and I'm measuring amps, and I am sitting at the 30 scale, so this is directly at 10 amps, basically 10 amps. Okay, guys, any questions about the analog? We'll talk about the analog, the principal operation for the analog in a second. I just want you to, I'm sure you guys have seen the labs and so forth. Look like this. Okay, let's go open the cover. Let's cover and look what's inside it. The mother, depending upon your point of view, of all analog and digital meter, this baby right in here. The operation for this one, guys, we equip the arson valve meter. So the operation, guys, for this one is very simple. Let me go energize that baby. We'll bring a DC voltage. This is a DC meter. Bring a DC voltage. I bring DC voltage to this line, and the negative here, the positive here, or vice versa. Now, my friends, I bring a DC voltage. I create a pole. So, long or short, you have a pyramid. Look at how they do it. They have, and just imagine, Eric, how people created these long time ago when you know any electricity. That's what always bothers me. They created, this is an electromagnetic equation, electromagnetic phenomena. So they have a permanent magnet. So here's my north here, and here's the south. Suppose this is my north and my south location. Permanent by permanent magnet. And so I put my voltage, guys, across this coil, and I create. You guys put a coil, put through a coil. It creates an electromagnet. Everybody knows that, right? Every time you have a piece of metal over here, and if you wrap around it with a coil, right, and bring a voltage here, DC or AC, you bring a 24-volt DC, you got yourself a north and a south. You get yourself a magnet, north south. My daughter was playing with one last week. So that's basically the principle of operation. Very simple, guys. We use all the time. Very simple electromagnet concept. So by the time, say, suppose we have a 24-volt here, and we need to measure this 24-volt. So you put this north and south. Well, guess what? Guess what? You're going to create another north here and a north here. I don't know about you, Eric, my friend. If you put a south pole of a magnet close to another south pole of a magnet, what do they think they're going to do? They're going to push away from each other. And that's the principle of magnetism as we studied, guys. I poles push away from each other, and different poles attract each other. So long story short, these two guys are going to move away from each other, and the deflection, how smart they are. It always amazes me how smart they started. That deflection, guys, right in here, when it moves, so you capture the movement. That's all you need to do. All what you need to do is just capture the movement, and now you scale that movement. So you capture the movement. Now, energize. Oops, I got my movement, and this movement will be scaled. You put your scale right in around here, and guess what? You got, and then you calibrate it. So at this point here is 0 after you calibrate it. At this point, 300 volts. So all you do, you capture the movement, you calibrate it based on different voltages, and go. You got yourself a voltmeter. You got yourself a voltmeter. You need to retard the pointer, guys. So they put a spring over here. So when it pushes, it gives a counter force, just counter force to retard it, bring it back to its original location, and not moving it too far. So, well, the most part, bring it back to this original location. So that's, you get yourself the mother or the father of all meters as we know it. Be it, guys, be it voltmeter, be it ammeter or ohmmeter, no problem. So as long as you create an electromagnet, they interface with another magnet that's electromagnet or non-electromagnet, and you capture the movement through a meter, you scale the movement, you calibrate the scale and the meter, and then you retard the movement to a spring. You get yourself a beautiful meter. Beautiful meter. Any comments? Any questions, my friends? So this baby is the father of basic the arsenal meter movement, the father of all meters, as we all say. The father. Any comments, guys? I can't emphasize. I'm going to be explaining it, guys, when you use the meter. It's really nice to understand how they started by creating that north and south permanent, and also north and south electromagnet interface, capture your movement. This is, Jason, my friend, one of the most important advantages of electromagnetism. Electromagnetism, guys, created transformers for us, created motors for us, and our advantage of it creating meters, the old analog meters, old meters. Basically, a couple of others. Then the smarter than Chad guys start using different meters, vein, concentric vein, and plunger charger. And I want to share my, I don't think we have a picture of them. I want to show you guys my desktop with you after I set myself on the right location here. Okay. And look at these. Here you go. Let's go. Share monitor 2. Okay, back in here. Minimum. Okay, I share these pictures with you. I thought they're really interesting. I'm gonna rearrange you guys on my screen here so I can feedback. Okay, get your chat. So it's in any of your chats. All right. Okay, one here. Okay. All right. Okay. Session. Okay. So this is the original meter, guys. As you said, I can emphasize that this is actually DC. This here is a DC. See if I can grab my. Okay, use it here. Then I know I can't use that one here. So I grab that one. Okay, so this is DC meter, which means, my friends, you need to convert. If you're to measure AC here, you need to build the bridge here. That always gives you positive in one side and negative in the other side. As you can see, this is the rectifier that can rectify a single a wave like this into a smooth, very smooth. Well, this probably will look something like this. It's very good, not the best AC, but it rectifies it into a smooth non-AC. The reason behind this is because you always need one side to be north and one side to be south. It keeps living and you wouldn't get any movement. So this is a DC meter. Moving on, guys, into a couple of areas. Where's my tab? Where's my? I thought we have them. No, I have a picture of them, but it's no, I don't. And you guys have there's meters. Let me close that one. Why didn't help me? Okay, if you guys go to page, I don't have a picture of it. I don't know why I don't have a picture of it. Usually we do. And if you guys go to page 249, same concept, which is radial vein. In the book, guys, 249 is radial, and radial, guys, is what it has two plates over here, and you guys they have stationary and moving veins. They have veins, stationary veins and moving veins. My stationary veins, and this is my moving veins right in here. And energize, you put your coils, you bring your power right in here, usually, and then your power. And as you bring the principle for work of, guys, radial vein is you create a magnetic field that deflects and will be captured through a movement. Let me just say this is my okay, there you go. And this is my let's go capture the movement through an indicator like this. Anyway, you create a magnetic field, guys, that interact between this location here and this location and get you deflection. The whole idea, my friend Joe, is to get you movement, some type of movement. In radial vein, you get the movement through induction. You get the move to induction. The thing is, you create a magnetic field in this location. Let's just say this is a north and another north right in this, and then the moving vein will move. As it moves the indicator with it. Now capture the movement. And what you guys need to do, you need to capture the movement. So back to page 255, my friend Joanne. It's the one that is page Standard Book of Electricity, third edition. This is the third edition. If you have third edition, it should be in page 249. 249. 249. Should be in page 249. I don't know why we don't have them. Too bad. Shoot. So I honestly thought we have a picture of them, but when Dilmar updated the code, and so if you guys look at I apologize if you don't have the book, but page 249, you basically guys bring voltage right in here. You bring your voltage 240 volts, and you created a magnetic field in this vein, and that induces another magnetic field in the other vein, and by induction you create, like motors, you create the magnetic field, and then will move away from the other vein, and there's an indicator with it. As it moves, the indicator will move with it, capturing the movement. Then all what you have to do again, calibrate it, scale it, calibrate it, and off you go with one, guys. So they are basically the radial vein. The concentric vein is the same thing. You have two concentric veins, yes, and bring your power from one side to it. So here's my 240 volts coming in here, and guess what? I have my indicator. My indicator tied to, they tie the indicator to this indicator going in here. So, long short, my friend, you're going to create, as you energize it, you're going to create a north pole here, and with induction, you're going to create another north pole here. That's, guys, the same principle of operation for motors. If you motor, this is the same principle of operation. So you create through induction a magnetic induction, you get poles, or north and south poles, and if you happen to have the north next to the north, you get yourself some type of deflection, and it's all what you'd want, or what it takes to calibrate, again, one more time, put your cell in it, calibrate, and get your 0 point and your 500 volt point, get yourself a voltmeter. Versus the stationary vein. So are the ones these ones here are moving veins, and the other ones are the stationary. This one is stationary vein. That's too good. Any question about that? Really, the reason then why we spent some time on that one is really just to help you understand the gravity of metering. The gravity of metering is unreal. Through electromagnetic induction, you can capture a movement. If you can capture the movement and you scale it and you calibrate it, you get yourself a meter. That's always what metering, analog meter is all about. Carrying a movement, a physical, mechanical movement through magnetism, and calibrating this movement, scale that movement, and calibrating it. The same principle, guys. All of it, the same principle. I wish I swear I had. Here's my indicator here. I'm trying to be smart with my drawing here. Here's my. Okay, let's see. Get rid of that one. So this is my indicator. It's my indicator. And if you guys go here and grab plunger, this is called plunger. Mr. Plunger is going this way and take to here, and there is a coil. There's a coil right around here, induction, AC coil. Okay, that's how we capture the movement. went here and I put 240 volt. I put a 240 volt, guys. As you put a 240 volt, this is what they call it, the plunger. The plunger. Let me see if I can capture it right through the core, that plunger. You guys energize it. It creates a magnetic field, and that plunger moves in out of the coil, in or out of the coil. And guess what? The plunger is attached to this red plunger here. As in and out, it's attached to this indicator, which is that red indicator. Moves that indicator with it, and that's how they capture movement. And like I always said, you go now calibrate that, scale it, calibrate it, and off you go with a voltmeter, ammeter, or any type of meter. Any of these three vein, concentric vein, and plunger vein. Any question, my friend? Let me see what we have here. There's all the information in chapter 10. Which version do you have, Byron? Which version do you have? Of our book you have? I have the 3rd edition or 4th edition. That's why. I'm looking at the 3rd edition. Thank you, buddy. I'm looking at the 3rd edition, guys. If you have 4th edition, which is the newest edition, you have it there, but I can't remember. So you're right. 4th edition. Okay, this is based on the 3rd edition, guys. It should be in chapter 9. 4th edition. Are you guys all have 4th edition? 4th edition, all of you. Or here. Okay, 4th edition. Here. Oh, in 4th edition. The 5th edition now makes things more complicated here. This guy's the newest version. I don't know if you've seen that one. This is 2011, based on 2011, the 5th edition. I do it in the office, I'm done with it. So this is my first. It's not a whole lot. Okay, question is really I just want to capture. Okay, let me see. 4th is school sent off. So okay. Sent to the 4th, based on the 4th. Okay. Sorry for 3rd. What the heck should we do here? Dilmar book 3rd. Okay. 3rd page. Actually, I'm just looking at the 21.3, guys. The reference based on the 3rd and also based on the 4th. Based on the 4th edition. Now, just please, guys, look at wherever they are, the radial vein, concentric vein, and plunger vein. Just understand the principle of operation for them and what I'm asking for. Understand the principle of operation. Okay, question, my friends? Any questions? Questions about that? The key point that I will emphasize, and I can't emphasize enough, is analog capture a physical mechanical movement. As you capture this physical mechanical movement, and you calibrate it, you scale it, and off you go with a meter. Okay, 11 o'clock. I'm going to give, before I start, guys, talk about the characteristics of meters and so forth. Let's go ahead and now, what is it? 7 o'clock. Okay, 7:06, guys. I'll give back at 7:06. And you're talking about voltmeters, ammeters, hook them up, and so forth. Okay, you can check him, please, my friend. I just checked while we are on break here, guys. It seems they got rid of in 2004 and also in 2005. Got rid of this information here, so that's really interesting. I always like they got rid of these three, guys. I guess because the whole world is going towards digital right now, as we all know. But it's always really nice. I always really like the principle of operation. They kept this one, guys, to the principle of operation. That's why I remember the CD that I got is 2000 CD, and they got rid of all these pictures. So my sincere apology. We have not missed a whole lot anyway. Okay, on into the voltmeter. Voltmeter, guys, are very interesting animals. Voltmeters, you could voltmeter always, it's always measure the power. It's always connected directly to the source, connected in parallel with the source. We all know. So what they do that you have to completely understand what they do is if I have a power source, or suppose that I have these my 240 volts, and is my circuit all the way, and here you go, all these circuits going on. And suppose I'm going to measure the voltage across this resistor. So what I do is I go literally physically to voltmeter in parallel with the voltage that I want to measure, with the branch that I want to measure. Is in parallel with the branch, or in parallel with the branch. Question my friend Eric I always ask when I was in school, and I'm sure will probably come to your mind, is say, okay, Chad, here's the power coming, the current, I have 100 amps. Let's suppose we have 100 amps coming out of here. The 100 amp which amp are going to go through this resistor, this voltmeter. So if 100 amps, guys, 99.999 goes through here. So very, very small amount, and very, very small amount that will be 0.001 amps going through the voltmeter. So now the question would be, Brenna, my friend, is, Chad, how can you put two things in parallel and make the current, most of the current go through one and not through the other, right? I always asked this when I was in college. How on earth can the current, almost all the current, go through this branch and through this branch? The only way is I can control the flow of current. Anybody knows how to control the flow of current? You can control the flow of current with a tab. That tab is called resistor. If you increase the resistor, if you put two resistors in parallel, guys, let me give you an example. If you put two resistors in parallel, here's two resistors in parallel, and say I have 10 amps. I want the 10 amps to go right here. All the 10 amps to go right here. If I can make this, all I have to do is make this resistor extremely high, very high. The more higher that you raise the resistor, the more open circuit you get. Long story short, the current guys choose the smallest, the least resistance. So the current has reach a fork, and one side is going to give you a huge resistance, the other side is going to give you very small resistance compared to the first side. Well, guess what? Where the current is going to go? The current will abandon if I have a current over here, and the current is going to, almost all the current is going to go right through here and back. And that's basically the principle of operation in reality for voltmeters. So then, based on this principle, guys, what they do is they put a resistor in series with the volt source, with the coil, and so it's extremely high. It's extremely high. An idea, here's a few, and again, without getting into it, here's a few industry kind of standard. If you're doing a voltmeter, we have 20,000 per volt for DC, and for AC you have 5,000 per volt for AC. What this means, my friend, if I want to measure up to, here's my meter, here's my resistor with it. Okay, let's grab it here. easier. Here's my voltmeter. Here's my resistor in series with it. You always have to have a resistor in series. Guys, so the question would be, Chad, what the heck is this then? What is this? This one inside is the coil. That's going to deflect. Okay, so the resistor, here's the resistor. This resistor has to be extremely high. So if this is all this is a meter, as far as you're concerned, leads of this meter. Everything else is inside the meter. These are the meter leads. So up the point. So suppose I want this one to measure 600 volts AC. So find the resistor that has to go with it to make it high. I need 600 guys multiplied by multiplier that we did. Okay, here, not here. Okay, multiplied by 5,000. Multiplied by there you go. Multiplied by 5,000. So long story short, you're gonna end up with 30 here, and 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Just have 1, 2, 3, 4, 5, 6, 3 million ohm resistor. This resistor is going to be 3 million ohm. You see that? Can you see that? How this is the huge resistor. Current, actually, most of the current. When I go and tie something across, when my let me use a different color here. So I my load. Here's my load, guys. If I have the current is coming this way, that's what happens when I have a 10 amps here. That's why 99.999 or so amps go directly through this, and a very small amount enough to sense the voltage 0.001 amps go through the coil. This is my friend Dan, number one, because you don't want the current to go to the coil. It will burn. If the whole 10 amps go through the coil, it will burn it. That's number one. Also don't want to have any power consumption by the coil. So it's going to measure the exact amount of voltage, the exact amount of voltage without consumption, coil consumption of voltage or current, which is power. Any questions about this? Any question why the resistor in series with the voltmeter had to be extremely high, extremely high. So that's basically high, and as we said, based on these recommendations anyway, you're going to end up with these values. Comments, guys? Any questions about that? Any comments? Any questions? So basically, what we get the resistor 4 milliamp. Okay, so that's measuring, and now then you can have multiple scales, guys, and you get into measuring the scales and so forth. You now, based on the same principle, guys, all this, as far as you're concerned, all this is one device. Everything they're doing, guys, is inside the device. Now I can add more resistor, and see, I will bring to your attention, guys, here's my, basically my circuit is coming. These are all what you care about, coming from here. But based on where you connect that lead, if you connect that lead right in here, you got yourself 30 volt scale. If you to here, you put 60. If you move it up to here, 300. All the way full scale, 600. And in reality, then what are you doing? You're adding resistors, The voltage, the more resistors you need to add. The higher voltage, the more resistors that you need to add. Because we need the branch that has the voltmeter, guys, to have extremely high resistance. So only very, very, very small amount of current can go through it, just enough to do the measurement. The deflection, all what we need is just deflection in that coil, a coil that makes deflection, so we can capture it to do the measurement. We don't need anything else. Any comments, any questions about that? So that, and then of doing the deflection, guys. Deflection. We have an example that it's 50 microohms and a volt of 1 volt to deflect the pointer full scale. So they have an example, and I really don't want to go through the whole calculation, but if you're using the 300 scale and you need to find the resistor circuit, I mean all the way. Now this is my circuit, right? Up to this point. Don't forget there's resistor here and there's resistor here. And yeah, by the way, don't forget that there's a tiny little coil that you get your movement. So there's and it's like this. The coil is going to take 1 volt to deflect a full scale, and the rate of the voltage is going to be, which is 299, right? 299 volts is going to go across resistors. So if you take the 299 volts, this by point, what is it? What did this use? It's 50 micro, and these are all calibration 0.00012, 3, 4, 5. Okay, so if you have 1, 2, 3, 4, 5, this is okay, so this is 50 micro, 50 over 1/2 million, basically 50 over a million. So if you do that, I'm going to tell you, and you get yourself a 5.98 million ohm. Long story short, my friend, without getting into the whole 80 video, guys, Dan, my friend, and why did I use the 50 micro? This is a 50. It's 50 micro million amp to deflect the voltmeter full scale at the 300. So if I want that coil to move the scale, I need 50 microamps going through it. Okay, that's my point. And I need 1 volt across it. So the over, guys, is going to be 299 is basically the resistor. So long or short, these two resistors together must, in this case, must be 5.98 ohm. You do some calculation for based on these resistors. I didn't spend too much time on it then because it's really good exercise unless you work in measurements and instrumentation. Doesn't have a lot of application in the power electrical industry. Any friends, any questions, any comments, and any comments? The same token, my friend, with token, you can go do the calculation based on the 30. If you're based on the 30, always remember, guys, one thing to remember about these babies, it needs 50. This by design, not by chance. The people who design it, microamps to deflect it, and also take 1 volt. It needs 1 volt to energize. That's all what this coil, which is basically nothing but a coil here. Remember, that's what makes the movement. This works on 50 microamps and 1 volt. I don't know about you, Eric, my friend. I don't know if you have a microamp in your truck that can measure 50 microamps. That's a heck of an ammeter to measure 50 microamps. On that's your start point, guys. If you want to find this resistor right here, piece of cake, Chad, the scale is 30, then this resistor has to have 229 volts. 20 volts, and divide 29 volts by 50 micro, which is 0.000. How many zeros? 1, 2, 3, 4, 5. There you go. 1, 2, 3, 4, 5, and 50. 0.5. That's the micro. I am to find these two together. We did them, guys. That will get you 290. Get you In this case, that will get you 59 because we lost one. Anyway, and you get the point. You start finding R1, then you subtract from R1, R2 to R1, you find R2, and then you do R3, and so forth. That they have a multi-range analog meter. Then, any, my friends, any questions, any comments, any questions, any comments? Reading multimeter, so reading the speedometer, guys, determine what meter indicates. The indicator of the meter, the full scale value of the meter, and read the meter. That's what we're doing. Suppose we're reading this meter, and suppose we are using we're using an ohm meter. I'm going to use a measuring ohm meter here. Ohms. Here's 0, and here's my full scale 1K. Sitting right in here, as you guys can see. So here's my 1, 2. This is 1.5. So this is 1, 2, 3, 4, 5. So this is 0.5, 0.6. So that will be 1.6 ohms. 1.6 ohms. And continue 1.6 right at this point. If I'm measuring this point and I'm doing a voltmeter, ATM meter, let's just say this point, and I'm doing, let's decide that we're using a 30 scale. We're hitting a 30 scale. So we have 20 here, friends, and we have 25 here. So this one in between is, oh boy, it's 1, 2, 3, 4, 5. This is up to here 5. So this would be 22.5. Isn't that? So it's 21, 22, 23, 20. So 0.5. So you're gonna have you see what I mean. You're gonna find how many. So if these are 5, this will be 1, 2, 3, 4, 5, 7, 8. I don't know if I'm reading it right here. 1, 2, 3, 4, 5, 6, 7, 9, 10. So each one of them as a point. So we have 10 points and we have 5. So 0.5. Each one of them is 5, I believe. So if you start with the 20 and a half, this will be 20 and a half, 21, 21 and a half, 22 and a half, probably 22 and a half. So you have to see the scale and see what the scale between these two guys here, if we're reading it, is 2. How many what these slashes means and so forth. So that basically, if you want to know how many of you guys use something like this, but the way I read it is always look at which scale are you looking at, and I'm jumping from in this case from 0 to 50. If I'm here, so that will be here 25, and then 1, 2, 3, 4, 5. So the distance here, we say 25 divided by 5. That's your 5. So each one of these is 5, 5, 5, 5, all the way. Okay. Any comments? Any questions, my friends? So that's basically we're looking at measurement, trying to find it. Any meter. Any about voltmeters? Voltmeters are very important concept, guys. Voltmeter. When you measure voltmeter, the most important things, as you know, is you always measure voltage when the source is on. You can't. Many people try to measure the voltage, especially in our school. Oh, I'm not getting anything. Well, did you turn the power on? You can't measure voltage if the voltage doesn't exist. That's the point. And the second thing, guys, is always when you measure voltage, make sure the voltmeter, always, we learn this from safety, the voltmeter is rated for at least the same amount of source or higher. So if I'm measuring at 13,800 volts, 1,800 volts, I think Verena, my friend, you're going to be using a 2000 volt meter on the system like this. Definitely not. So guys, more than over 1,000 or 600 voltmeters, the digital meters. So make sure that that you're using them for not higher than what they're rated for. 1,000 volts. I have my voltmeter here, Fluke, rated for 1,000 volts. So you can go up to 1,000 volts. 1,000 volts, yeah, relation and so forth. So that's basically what make sure that the rating of the voltmeter is equivalent to system voltage, if not higher. In parallel, you can't connect the voltmeter in series. You have to connect it in parallel. Now to another meter, very interesting meter, is the ammeter. I'm not going to ask you. This is guys from Ohm's law. It measures the current, which measures in amps. That's very clear. Unlike the voltmeter, exactly the opposite, guys. It has a very low impedance and must be connected in series with load to permit the load to limit the current. These guys exactly the opposite. I have a voltmeter, guys, and I have a source voltage, and I'm talking about about analog meters for the most part, DC. If I have a voltage source, as you know, and here's my circuit, and here's my other circuit, and here's my fourth circuit, and all these are resistors and so forth. If I'm to measure the current in here, folks, these are all just make. There you go. Let me just so we can. Okay, there you go. Connect these, connect these, connect these, connect these, connect these. So I am to go and measure the current right here. I have to open. Can you get that? This is circuit is closed. I need to measure the current right in here. The first thing to do is go open the circuit. Can you get that? And when you open the circuit, you're going to grab the wire here. See how we open the circuit? And here's my amp meter. You have to open the circuit and you connect it in. Is where you want to measure the current. I measure the current here. I want. See on the circuit? Now, I'm going to tell Eric, my friend, that you would never open a 4,000 amp switch gear. Do it this way. For DC, small amps up to 10 amps, guys. But we have AC 4,000 amp switch gear. We use the principle of clamp on ammeter. That's the induction. We use the principle of induction. Okay, we'll come to the induction, guys, in a second, but this is really an interesting concept. And I want to bring to your attention, guys, the meter has a coil here. And also want to make sure that there is a resistor, this resistor right here, that's the coil, in parallel. So here's what happens, guys. Suppose I am reading 10 amps here, and the amps came out also as 10 amps here. And could, as you know, 10 amps here, and continue 10 amps here. It's a 10 amp series circuit. So, but here, guys, what happens is a resistor. The current that's going to go through here, this will be very small, 0.001 amp. Current that's going to be through this resistor is going to be basically 9.9. 9 and 9, right? Do you need another 9? Another 9. So long story, most of the current, guys, look what happens. Most of the current is going to come here because this is very low impedance. It's going to come down here and come here, and only very tiny amount of current is going to go through the meter to get you a sensing mechanism. This is the opposite Brenner of the voltmeter. You need a resistor that is extremely low across the coil, so most of the current will actually be diverged away from the meter. Most of the current will be diverged away from the meter. And all this junk that you guys see over here, this is all this stuff is inside the meter. You don't see it. This is part of the building of a meter. Any questions, any question, my friends? And the only thing you need to remember is with an ammeter, you need a very low impedance, very small resistance impedance in parallel with it. And in parallel, because we will shunt it, we will the current to avoid, we will avoid moving the current through the coil. To do that, Eric, my friend, you have just burned that baby. If you let that 10 amp go through the coil, you have just burned that coil because it's not rated for 10 amps. Basically, yes, the very low impedance, we know what low impedance is, must be connected in series with the circuit. Not just with the circuit, you have to connect it with the branch that you need to measure the current with. When we do in our college, when they train basic electricity, people understand if you have a circuit as just sees a resistor here and a resistor here and a resistor here, and let's say the resistor here, resistor, and all these are connected resistors and so forth. If you want to measure the current, if you are to measure the current right in here, then you have to break these 2 points. Measure the current right in here, then you have to break these points. You're going to break this point and here and put your ammeter right in here. So you need to know where to break. Where to break is where you need to measure the current. So ammeter shunt, low resistance device used to connect most of the circuit, as I said, the shunt resistor away from the meter. The key point, guys, is to avoid dumping the current across the coil of the ammeter because you burn it. Here's the shunt resistor, as you can see, and very forward. If I am to measure a current, if I want to measure a current of 100 amp here, 100 amp, well, 100 amp, not 1,000 amp, Chad. Let's say 100 amp, and this is high, guys. Let's just not use something more practical to use. Suppose I'm going to measure a 10 amps here. 10 amps, guys, are going to be 9.999. I'm going to go here, and only tiny amount, which is 0.0002341 amp, is going to go through the coil. And I don't know about you, my friends, this is my coil. This one is the one that's going to deflect the coil and get the measurement. And when they come out, guys, here, they have to come up as a 10 amp. So can you know the current, the coil is going to see very small amount of voltage. So everything that you guys are looking at right in here is actually part of the ammeter. This part will be built in the ammeter. You wouldn't see it. You connect the leads of the ammeter here and the leads of the ammeter here, and you adjust it. Any questions, my friends? Any questions about my meter? Most current will go from the ammeter. Most of that will go away from the ammeter. Okay. Okay. So there's an example of how to calculate this one, guys, in the book. I thought that was really interesting. Area need a 0.05 volt. Okay, so the 0.05 volt is to activate that coil, and then the rest of it is going to go across the coil. So 0.54, and then if you need to find it, you just take the 0.05 volt divided by the current that's going to go through it, and that'll show how small the impedance is going to go. So, for example, they're telling us, guys, for one to work, you need 0.05 volts. Line. So who is this one, friends? The designer of this coil. They're telling you they need 0.05 volts for this baby here. Which baby, Chad? This baby here to pick up. Okay, so that's the 0.5. And you, my friends, That's the voltage. And if you think the current that's going through it, and suppose um, that's, so if we divide this one by the amount of current that's going to go through it, 0.05, you can find 9 milliamps carry, 9 milliamps carry flow through. The resistance can be 0.99. 0.9. So suppose that we just take example that they're using. There's 1 milliamps here, and 9 milliamps here, guys. So to find the size of this, resistor, you take the 0.05, right, and it by 9 amps, which is 0.000 9 milliamps over 1,000. Okay, 0.009. 0.0. If you divide 0.009, if you divide by 0.009, guys, look how small the resistor that we find. 5 resistor will be 5.5 ohm. You can see how this resistor has to be very small, so the majority of the current will go across it. Okay, I'm going to stop without getting too much into the details of that one. But that's a method, guys, of calculating the resistor. Any comments, any questions before into the multi-range ammeter? Multi-range ammeter, guys, can give you different range by having different shunts. Connected, as we know, shunt. There you go. So that's basically that the shunt. So what they do, guys, is they have multiple. Here's your meter coil. It's all the coil, guys. Is coil, and they have multiple resistors. And pick and choose where to attach your coil to. You can pick here, or you can pick to attach resistor here, or here, or here. So that's your picking point. And you put certain resistor across that coil to different range. Whatever you do, the shunt must never be disconnected. With junction, these are all connected, guys, and must be disconnected. And a few multiple guys examples. Here's one of them is called the shunt to meter make before break. 10 shunt. Let's look at them here. We don't have the picture. Here's the connection is made to different parts of the shunt, and the meter movement is never disconnected from the shunt. Switch connections are made external to the switch. Here's I think we have make break. This is guys in page 62 in my book, meter, and you can see how the shunt make the break, and you never leave the meter without a resistor across it. That's kind of the key point, is never to leave a coil. Never leave a coil like this. You always have to have some type of a resistor, burn it, some type of a resistor across it. Whatever you do, that's kind of the key point of this metering. Resistors. Here's how we can find the resistor without getting into the details, guys. The R resistor. In here, you take the amp. The amp is the current of meter movement. Rm is resistance of the meter movement, and resistance of the shunt, the added resistance. So the resistance, find how much current you need to make to energize that coil. What's the resistor of that coil? Off you go. I think there's so R equal I M. The meter movement, R. Okay, so the current of the meter, current of the meter movement, total current, IT, which is 0.01. So this, I'm sorry, gentlemen, this should be the IT, I total. No, that doesn't make sense here. I total. So equals the current that the meter needs divided by the RM meter divided the total current that's going through the circuit. That's the current that's going through the circuit. So if I have 1 milliamp, that is the current that's going through the meter. There is 50. So that my resistor is 50. What is the 50 ohm? My meter amp that I need is 0.9 little amount of amps. 0.001. So that's 1 milliamps. Divide this by both that my total current that I need is 1 amp. My total I need is 1 amp here, and this will get you, get me 0.01 times 50 will 0.05. So the resistor has to be 0.05 across the coil. The resistor across that coil have to be 0.05. So that's basically, I really don't like to spend too much. There's a lot of monkeying around. We do it in technical colleges. We monkey around a lot. There's a lot of calculation, guys, how to measure this one. The key point is always remember the current that you need to deflect is 1 milliamps. The resistor is 50 ohm, and then you can size all these shunt resistors based on this principle. Please change this one here into I-total. I-total. So I have my coil. Here's what we're trying to say, guys, here. If I have a coil, here's my resistor that I'm trying to find across that baby. Here's the current that enters the system. A current of, what did we say? A current of 1 amp here entering, right? Coil need is rated for 50 ohm. I bought coil this way. Don't ask me why. And the amp that's going through this coil is 0.001. So the question is, what size resistor do I need to put across this coil? That's what we're trying to do, guys. What size resistor do I need across this coil? That you take the resistor of the coil multiplied by the current that energize, activate, ignite that coil, and divided by the total current that enters the system. In page 64, 265, guys, a bunch of analysis how to find the total resistor for multimeter. So it's not worth it. With it. On from the DC, most of the stuff that you guys did are DC. These are all measuring DC stuff. Moving into AC, with the AC, it's really interesting. Instead of shunt ammeter, now we have a current transformer. We have a current transformer. So the transformer is connected in series with the load, the primary of the transformer connected in series. The ammeter is connected to the secondary of the transformer. The ammeter is connected to the secondary of the transformer. So that's really cool when it comes to the AC. Now we're doing AC, guys, and AC take the advantage of the transformers. Here's my transformer. It is my transformer. Here's my other transformer sides. So here's my coil. This is just one way. Here's my coil. That coil that I only energize for the meter. Put it in this side. And here's the current that's coming through this transformer. The current that's coming through this transformer might be 1,000 amps. Look at that, 1,000 amps. But it goes through the transformer, guys. It will come out this side as a 5 amp. Look how nice it is, 5 amp. Now my coil can handle that. No problem. I can't put 1,000 amp across my coil and stay in business. So this way, then the turns ratio, what they call it, guys, the turns ratio, we take the 1,000. Let's start the primary. The turns ratio, which the secondary is 5, divided by the primary is 1,000. 1,000. So 5 divided by 1,000 or 5,000. Say 1,000 divided by 5. I'm losing my mind here. 200. So basically, the ratio, guys, that for this transformer, current transformer, as when we do it, let me just grab that one. The current transformer, um, the one, every 1000 amp will be seen on the secondary as 5 amps. So 1 amp here in reality will be seen by how much? 200 amps. So every 200 amps here will be seen by 1 amp. That gives you a ratio of transformer. That's the only way, my friend, guys, we can measure high current. If you have a 4000 amp switch here, a bus 4000 amp switch here, how do we measure a 4000 amp switch here? You're not going to put it through a coil. Through a coil, what you do is you have a CT. You familiar with the CT current transformer? I take this. Here's my bus. The current right in here is 4000 amp. You have 4000 amp and change it into 5 amps. So what that means? What means every time there is a 4000 amp going through the cover bus, it will be seen on the secondary of that CT as 5 amps. So what do? I go put it across a meter, amp meter now. Every time I see a 5 amps, it's actually calibrated as 4000 amps. Now you do the ratio. If I cut, if one time, look how it works is, say if I have 2000 amps here, see 2000 amps, this will be cut by half again, and I will see on the meter 2.5 amps. So now I have half of my amps in my system. Okay, that's basically how you find. So this will be yeah. So that's basically how you can. If you just by, let's take the 4000. Take the 4000. This one, I'm just going to go by 5. So both that you divide this, you have an 800 amp moving in here. The 800 amp will see your 800 amp. In this case, will be seen as 1 amp here in the system. So, guys, about how the current transformer takes care of business. Current transformers are not or transformers, guys. Current transformers, their job is to transfer current. They're not supposed to transfer power. Based on the principle, the higher the current comes in, the more the less amps in that particular site. That calculates the meter. CT is commonly used, and you can find a CT that can convert 200 amps to 5. Rated for 200 to 5, so you can load them up to 200. If your system is higher than that, then you go 400 to 5. If your system is 100, you go 1000 to 5, and the way up to 4000 that we install a few of them, 4000 to 5. It's industry standard in the American system that is on the secondary always 5. On the secondary is always 5. The primary can change. I can have a 4000 amp CT, but if you are to get what the secondary has to be, it would have to be 5, because the equipment that we have cannot handle more than 5. And JC, my friend, to work internationally, use 1 as a matter of fact. They use their secondary is 1. So it's standard. It's basically standard. So having a secondary of 5, always designate operate with the secondary windings. That's basically how we do it. This, guys, is the same principle of the principle of induction, guys, work. I have I'm sure all you guys have, this is an insult or not, but I have ideal, so don't laugh at Chad here and say, Chad, we don't use Luke. Luke, I have ammeter here. You guys have used it. It comes a clamp-on ammeter, clamp like the one that you're using, and I go with this ammeter at 600 volt. 600 volt, I can go up to 1000 amps. Up to 1000 amps in this baby at 600 volt. So that's all what you have to do is you come on ammeter and you read, and it will get you the measurement, the actual measurement of your amps, the actual measurement of your amps. So no disconnecting. The nice thing, Gerald, my friend, about these is you don't have to disconnect the circuit, as you can see. No connecting of the circuit in any way, shape, or form. So how does that work? Let me just quick review. This is what you should wake up now. Suppose I have a current going through this motor. Suppose I have this motor was, let's say this was 100 amp motor, 100 motor, right? You can convert it to horsepower, but let's just say 100 amp motor. And I brought and this was a 120, so I brought the current back in here. So as when the current goes through the 100 amp going through the meter, it will convert it from 1 amp into 5 amps, CT, that CT that you have here. Then it dump it. This is the CT. You can see that this is basically a CT. It's into 5 amps. And Gerald, my friend, when it converts it to 5 amps, it dumps it across this electronics, and then takes it from AC to DC and dump it across all these digital bridges and so forth to convert it into digital system. But the key point is taking this huge amount of current and minimize it relatively into a 5 amp so I can handle it, into amps that I can handle. So, yes, any question about the ammeter? This is basically what you're going to be using. I'm sure a lot of you guys use these meters, the good ones. Guys, I mean, 1,000 amp is not too bad. The true RMS hour, that's an ideal one, but you can have a fluke or any one of them. This particular one, guys, you can measure 600 volt DC or AC, as well as 1,000 amp AC and 1,000 amp AC. So that's through the induction, through the induction. And that's exactly what you guys are looking at. Exactly what we have now, slightly different than the one that I have here. Okay, so you can measure again DC or AC, both or AC, current only AC, and this one that I have, true RMS AC. But you guys can get your AC or DC. So you can AC or DC a clamp on and meter. Basically, with the digital ones, ohmmeter. Before we move into the ohmmeter, guys, ohmmeter always measures resistance, as we all know. Key point: ohmmeter needs a power source. I can't believe, Jacob, my friend, how many of my students burn their ohmmeter, multimeter, because they connect it hot to the circuit while they're doing ohmmeter. So you measure the resistance to series ohmmeters and shunt type ohmmeters. We'll talk about this one, guys. But the ohmmeter, which is R, a little bit about the R. My friend, R is a natural phenomenon. A natural phenomenon means you can measure it without connecting to our source. So, guys, when we measure resistor, we energize the circuit and we power the circuit, the resistor, with our own power, battery power, to get the current to flow through, and then from that current that generated by the resistor, by the power, the power battery, we can get our measurements. Long story short, you need to de-energize the equipment if you measure it. De-energize the equipment basically before you measure it. That's ammeter. We have a few terms right here. We'll talk about this one in a second here. Ohmmeters. Okay, so that's my meter. High voltage resistance. For resistance to be measured, the ohmmeter always you have zero. Always we learn, guys. When you measure resistance, always zero it. So select the zero. Then connect it, then move it all the way to the resistor before you start. Before you have anyone involved. So if it's a series, as we said, look at the difference, guys, in series. If you put in a series, we have, I think I don't have a series resistor, shunt type or ammeter. and series ammeter in page 277, guys. And I don't know what your page would be on 2004. You have a series resistor. One resistor, it can give you a much high value of resistance. If you parallel them, shunt them, you can get low value of resistance. Exactly the principle of operation of ammeter shunt and shunt. So that's what the principle of with the digital guys right now is really not a whole lot of things you can do about it. It's unknown value of resistors in parallel. Meter movement cause part of the circuit to bypass it, and that deflection when you put it in parallel, that deflection is captured because of the existence of this resistor, and calibrate it and scale it. You've got yourself an ohmmeter. Ohmmeter. Just a few reminders, guys. A few, as I said, series or shunt with the digital meters. I have my fluke here too, just for you guys who are fluke guys. This one is a good one for certain measurements. If fluke can get my ohmmeters, so this one, guys, you can have voltage up to 1,000 volts, 10 maximum use. It's with series. It doesn't have clamp on the ammeter here. You can buy a piece with it, and you can measure a lot of sensitive. It's very sensitive for you can measure a lot of from that piece of it. So anyway, so that's basically ohmmeter, digital ohmmeter. We have a few analog meters. I don't have them in my office here at home. We have them at Dunwoody. Sometimes, guys, we can measure milliohm and kilo ohms and micro ohms based on how you put them in series. Again, get you a high value, or you add a couple of resistors in shunt in parallel to get you a low value. Any questions, my friends? Any questions? Any comments? I can share the resistors, these pictures for you. I think I have some of them here. So quick, I know you're due for a break, and I will give you a break, guys, in less than a second here if you hold your horses. Okay, so what we talked about the meter, guys, and the batteries. See, these are okay. Ohmmeter, we talked about this one. Okay, talked about that one. Meter with loads. This is an analog ammeter, guys. It's pretty interesting. We have a few of them in our offices. Shunt. We talked to calculate the shunt, guys. Shunt with the P. Look at the current. How most of the current goes away from. Most of the current goes away from the meter, and only very small amount of current goes through the meter. Otherwise, you're going to burn it. Here's what to show you guys. I wasn't able to. When you have an ammeter, a DC ammeter, multi-range, they always make before break. As you slide this, it will always be connected, shunted. So always be connected. Always be connected. The reason behind this is because they don't want you to burn the coil. So that the key point is always all connected. Make before break. And how do they do that? By manufacture. You slide it cover piece that shunts all these. Can you guys see that these are all resistors in parallel? And you can see that all these are resistors in parallel. So as long as you connect to one of them, you are putting a resistor. So if I'm connected here, here we go. If I'm put it right in here, at all times, wherever you go, you're always shunting the coil. You're always shunting the coil. Okay. These resistors, calculation. There's a few calculations, guys. Go ahead and fuss around with it. Not a biggie. Calculate the DC. Okay, here's what current transformer, guys. For an AC now, to get you different ranges. That's what I wanted to show. Instead of having resistors, what we do is we have a transformer. Can you guys see that? Here's my transformer, the transformer. Okay. And what they do, the smart and Chad, they go change. If you want to change the range, all you have to do, literally, physically, go change the coil, hook up to different coils. So hook up to this coil, as you guys can see. If you hook up, look how this is the range. Every time change the coils, you got yourself different ranges. How they get multi-range ammeter? They basically have let me just drop that coil right here, and basically what you're tapping into in different parts. Here's one part, here's another part. You adding coils. By adding coils, it will get you more or less current. That coil and adding it. Okay. Let me see here. Yeah. All right. Any question, guys? Anybody has any question about that? Any friends? Everybody can see if I can have feedback from you guys. Move on. This is an interesting one. I like the visual because it tells you if you have 1000 amp going through your circuit right now, through your load. Is my 1000 amp going over here? Well, guess what? Secondary of the transformer, when it transfers, oops, let's go use a different color. When I transfer that baby in here, it will transfer through the induction. This is an induction, and it will be seen as 5 amps. That's why I don't burn my coil. These guys are very, very important. You find them in every switchboard almost. One thing is here, I don't know how practical this is, but what they did, they looped. So suppose, and I really need to do that. Look, they did. They went and they looped the 2 turns inside it. Instead of turn, it's going twice. The current is going twice through it. So the current here was 1000 amp going through the whole system, guys. 1000 amp. It will loop it. If you loop it, you are and this basically this C was a 1000 to 5. If you do loop, you got it by, so now you have 2. You do, this becomes 400. If it's 3, you divide basically the 1000 by 3. You loop it. So if you put 2 turns, as we said, your first one end, as you can see, one loop instead of one, there are 2 wires coming through it, coming twice. Can you see it? Came once and came again twice. Now suppose you guys go and bring it 3, let's just say 4 times. You loop it 4 times. So you divide 1000 by 4. That will get you a range of 250 to 1, so to 5. Now, friend, you are looking and say, why would I do something like this? That would be more sensitive equipment. A 1000 to 5, guys, is not good sensitivity. If my full load amp is 50 amps, it's sensitive. It's not sensitive enough. So to change the sensitivity of the CTs, what you do, which is not practical, is to loop them, and we never do that. What we do in a good term, guys, is what we do, like engineers and designers and all the stuff. If I know that my switch gear is 1000 amp, I just buy a 1000 amp. If I know I'm dealing with a 500 amp, I buy a 500 amp to 5, 200, 250, 2. That's what I normally do in major equipment. I don't know about you, Brenna. I can't lube a 500 kcm here. Can you? 500 kcm lube it? kcm? Are you kidding, Chad? We're gonna lube that one and maintain the bending radius based on the code. It's impossible to lube it. So this is for guys, small conductors. You're talking about number 8, number 4, number 8, number 6 if you're stretching it. You're not going to be able to do a 500 kcm conductor a little bit. But a little bit you cut, you increase the sensitivity of the CT. Thanks, guys. Any questions about that? Any questions? So I wanted to show that one where we'll bim. I don't know if you guys can see that one. The voltmeter. Okay. Voltmeter. Okay, transformers. Movement. This is for the coils, guys, in series, arms in series and parallel. Meter resistance. Okay, I'll stop right here. I really don't what I wanted to show you is the loop. Okay, let's guys go ahead and take a quick break. What is it? It's 8:07. Oh boy. 11. Let's say 8:14. Would that be good for you guys? 8:14. Give you 7 minutes, and we'll go from there. Okay. Okay, you can check in, please, friends. Okay, then next is we're gonna go talk about basically what's most practical right now, which is digital meters. Um, Before I go ahead and start, how many of you guys use digital multimeters? Let me see. Digital multimeters, use them. Sure, you use digital multimeters. You probably use Ideal or Fluke, as I said. A good version, probably get yourself a 1000 amp clamp on ammeter with a close to at least 600 volt DC AC. That's a great meter to have. You can measure your voltage, you can measure your amps, and for the most part, what you need, guys. You can have ohms, you can ohm it, you can range the circuit, continuity, and so forth. Amp meters, guys. What I'm going to do with the digital amp meters, share a few, just desktop and a few slides here with you. Go look at the way now. The way the digital amp meter, guys, works is you find a current generator. Look at 5 volt, no amount of current. You have 5 volts. You put it into a current generator, and the current generator drops that current across 5 resistor. And electronics, this and then this is very simple way of looking at it. Through a lot of electronics, guys, and transistors and so forth, converts it into digital, and digital certain certain lamps over here to indicate the amount. So I'm not going to get into the whole how to convert it, but the key point is to capture it as a current, capture that value as a current. A couple of them, look at this is multimeter, guys. Look at the interesting volt. So suppose that I'm connected to I'm going to connect right in here and right in here. This is my voltmeter, and I so volt and volt. So suppose just think of it. I have 1000 volts over here. The 1000 volts, guys, will translate over here. You can see you bring it over here, go back. Now I rectify it. Can you guys see how you rectify it right through here? And you dump it across an F18. This is a special type of transistor, and you dump it across this. Now you have crossed the analog to digital world. You get it in here, guys, and through all these electronic circuitry beyond the scope of this work, convert that 1000 amp, 1000 volt into it reads 1000 volt over here. So, guys, there's a lot of resistors here, a lot of ranges to get you the range, guys, whatever range you want. So then, this is just to control range. This is to get you the DC. This is my DC over here. Convert to DC. This is range. And this one is basically move it into a digital world. Digital. Convert to digital numbers. So that a voltmeter and the ammeter will act exactly the same. So that's basically without getting into all the details, I always like to show that we have a multi enter Claremont and a good voltmeter Fluke that gets you really good of volts. This is 1000 volts, 1000 volt measurements. Okay, so this important things, guys. What we call it. This is the high. This is a high impedance device. And it vibrates. I don't know. I'm sure a lot of you guys have this one. The good thing about this meter is really doesn't need a battery to operate. All it does is if you bring a voltage right here, voltmeter, suppose this is a 240 volt, it has a plunger that has an indicator here, and if it moves up to 240 here, be scaled up to 240 here, 120 here, say 40 volts here. That plunger moves up and down to indicate, and that indicator will move with it to indicate if it's 240, 120, just different levels. A lot of you guys use it just as an easy way of knowing if the equipment is hot or not. It's not accurate in terms of measuring the voltage. It just tells you, is this voltage 480 or 240 or 120? Basically, that's all what you, is it hot or not? So you guys energize this, you create a magnetic field. The way it works, and energize this coil, right? This is a coil. It creates a magnetic force that pushes this coil down or up. It will be pushed up or down based on the amount of voltage that you dump across this coil. Really easy, simple to use. Misleading in terms of accuracy. It's just meant to, at least to indicate a very easy way of sensing do I have a hot wire or not. Do I have a hot circuit or not? That's basically it in terms of the meters. Any question, guys, about the high voltage? And this is what we're talking about, guys. High impedance. You from here to around, you get you a measurement to a certain level measurement. So, questions? How many of this? Anybody have a device like that? It's some grades. Anybody has it? Get you the voltage? No? I'm sure you guys, probably a lot of you, you know, if I have a good picture of it. Yeah. Page 285 again. I don't know what's in yours, guys, but it's voltage tester basically. It's really it's not measurements. It's just a test if voltage is there or not. Voltage. Low voltage tester and unit voltage testers. Okay, that's just voltage tester to test a voltage. Missing is usually get you a object reading measurements, but it really means to get if you have a hot test if you have a voltage or you don't have a voltage. Come handy because you don't need batteries. Okay, any question, guys? Any questions about the voltmeter, ohmmeter, ammeter? If I summarize, Jacob, my friend, I hope you can get away with a few things tonight. You can get away as the digital meters are the kings. You need a digital meter. When we measure the voltage, we measure it in parallel across the load or the source. When we measure the current, we measure the current in series. And guess what? In series means you need a clamp on a meter. This is in series means so I have, if this is my 4-aught conductor, I put it right across it. And by putting the conductor across, I create a magnetic field that induced in this coil, basically a CT, current transformer, which translates inside this digital into a value, an amp value. So moving on, the one for the last, guys, just move on for the sake of the time here. Oscilloscope. Who guys use oscilloscope? If you guys use oscilloscope, oscilloscope is not meant for high voltage, meant for my friend, and then in this VFD world where everything is DC and you convert it to AC and frequency is not sinusoidal, it's oscilloscope really nice way. Suppose you have VFD. I'm trying just to everybody knows the VFD, right? Variable frequency drive, VFD. Suppose you have a VFD and the output of the input of the VFD is a nice sinusoidal wave, right? Coming in, and the output of this VFD is a step voltage to control the speed, and your voltage is going to look like this, step voltage, right? So that's a good way of looking at it, and it's not working or something. An oscilloscope, guys, would be able to draw these for you, measuring the voltage for you, and look at the voltage range. You draw the voltage, and on the oscilloscope, you will see a signal that looks like this. Okay, that's how it should be the input. So my in here, and my output for this device should look as a step voltage coming to the motor. So it's not looking at like this. This means there's something wrong in the DC rectification of the signal. Anyway, voltage during a period of time can be analog or digital. They both the positive and negative voltage. Here's the positive voltage here, and here's the negative voltage. So it shows you the shape of the voltage. The shape of the voltage. Voltage range, you can adjust vertical. You can adjust it vertically, guys, like this, or you can adjust horizontal, which is the time. This is the time, and this is the voltage. So you can adjust the signal vertically and horizontally in the base. Frequency, we all know, guys, is 1 over time. So that you can adjust the time. By adjusting the time, you can adjust the frequency automatically and displayed. Also, another advantage of it is the ability to measure the frequency of the signal. So by measuring the time, guys, as we say, here's my signal. If I measure the time here, from here to here, and take 1 over the time, guess what you get? 1 over the time, you get yourself the frequency. That's what the frequency is. Definition of the frequency, 1 over the time. That it takes 1 signal. It takes 60 circles in it. So here's 1, here 60 is in 1 second. So the time is 1 second, and 60 signals, the one that you're looking at above, to give frequency to 60 hertz, right? So time, the signals is 60 divided by the time, 1 second. That'll get you 60 hertz signal. And figure if your frequency is screwed up by measuring it. And probes, you have your probes that bring the signal into the device. Like in anywhere. We have a few things in the oscilloscope without getting too much into the oscilloscope. We have the power to power. We have the beam finders. I don't know if you see a beam where it's going to show your ground. We have probe adjustment, intensity, and focus function. You can bring 2 voltages. You can bring a current and a voltage and look at them side by side. Channel number 1 showing a voltage that looks like this, and channel number 2 that show a signal that looks like this. So that's an indication you have harmonic. And alter chop, you can adjust chop, add the signal to another signal, the ground, the position, normal, level, scope, and so forth. So there's an adjustment, guys. But the key point, and I thought I was in college, but like you probably, guys, the key points that we did when I was in college, at least, you adjust the frequency by going this way, and you adjust the magnitude of the signal by going the other way, up and down. And then, of course, based on the frequency, and you can, based on the time, you can find the frequency. Any questions about this oscilloscope? Questions? Dear friends, you might be laughing about oscilloscope. I talked to an electrical contractor who is a member of MEA. He told me he kept himself busy during recession by fixing VFDs. Instead of installing them, he goes to the customers. The VFD sitting on the bench, nobody knows how to fix. So he goes take it and charge them a certain amount of money and fix it and install it for them, and fix VFDs and so forth. And oscilloscope becomes very handy to look at the signals and so forth. So that might be far away from what we do. Having waveforms, this shows voltage in respect to time. With waveforms in a scope takes time and practice and all this good stuff. I mean, when I use it in college, guys, the only thing I can see in part where it becomes a value, if you're troubleshooting anything that has DC conversion to it, it becomes a big value to look at the signal and see, is the signal, as I said, it's supposed to be a step voltage like this? Why not? So maybe a diode or a integrated circuit burned. Maybe if we can buy this integrated now, Now we're going down to the component level, device, not equipment, down to the component level, electronic component level. So we might be able to change it, and off you go with your step. Okay, so I wanted to show a few. I think there's you guys have probably been to a few slides about oscilloscope. As you can see, this is what we're talking, guys, about the voltage. You have voltage this side, and you got yourself time or frequency on the other side. You adjust them. AC square wave. I don't know if you can see the AC square wave, guys. Here's my AC square wave. I don't know if you guys can see it coming here. Okay, so that's probably an output of the VFD. So that you can easily look at the voltage output of the VFD that looks something similar to this. And the alternative, guys, the alternative is sinusoidal. If it's not VFD, probably it's going to look something like this. Right, to sharp for me, sinusoidal wave, right? Sinusoidal wave. Okay, by looking at the signals, you can tell if there's a screwed up electronics or not. This is, as you can see, these coming all the way at the bottom here. This is a chopped DC wave. You know, I mean, some chopped DC up, flip it, and so forth. So you can get rectification. As I said, it's really cool to look at the whole rectification system. We look at the rectification system. Okay, moving, guys. Okay, to the wattmeter. So the last very important concept, guys, is measuring the power. How about you, Byron, my friend? But we pay, when we excel energy, we pay for power. So here's the power. Power is measured in kW or W. I don't know, Dan, my friend, we don't measure the power in kVA. kVA is we size system based on kVA. We measure power and we pay for power based on kW. Interesting concept. Really, guys, the basic concept of a power circuit. Suppose just wear this one for you, and we on the lab all the time. Suppose I want to, I have a source here, a power source here. This is my 120, and I need to power that one and measure the power that's going through it. So the first thing you need to do is you need to series. Look at how we see, guys, and here's my. Let's just go pick up my load here. So I tell you where my load is. Oops, we make it big. Here's my load. This is my load, my resistor going all the way back. And we want to measure the power that this resistor is consuming. And let's just go and use a highlighter here. Okay, here. You have to look at, guys, how I connected in series the current coil. Okay, I connected it in series, and power coil, the voltage coil, guys, as you know, you're going to be connecting it in parallel. So I'm going to tie it here, and from this side, I'm going to come all the way and tie it across this resistor. So by connecting this 1 meter, the voltage coil and the current coil, by measuring the voltage and the current, basically what I did, guys, this coil will measure. Suppose this is measure 10 amps going through it. Suppose voltage, guys, that's measured over here. Oops, the voltage right in here. Suppose measuring 120, like I should be. So it doesn't take a genius to do math here and take the 120 multiply it by 10, and that will get a healthy 1200 watts. So this piece of equipment, this lamp here, will consume 1200 watts. Well, so long story, my friend Jacob, if you are using an analog watt meter, you basically, and we hook them in the lab, guys, you're going to be hooking up two coils. One coil for voltage and for the current, and then you can see that this, and then capture a movement based on both the voltage and the current, and calibrate this movement. Remember, this movement now is based on two coils. One coil is the current, and the other coil is the voltage. And two coils will diverge move indicator appropriately to indicate the amount of power. So in a case like this, this will be calibrated as a 1200 watt. 1200 watt. So scale calibrated, but the movement this time, Joanne, my friend, is based on two coils. One coil, guys, is coming from here. You can see it. That's the current coil. The other coil, as you can see right in here, the voltage coil. These two coils will create the magnetic force that will shift both of them based on the current and the voltage, shift the indicator. And now you get yourself basically a movement based on two things, a current and a voltage. And in reality, you get yourself a movement based on the power. This is basically any comments of this. Basically the principle of operation of a wattmeter. I know you have a lot of equipment. I don't have a wattmeter, guys, but I can calculate the voltage and the current, and by multiplying the voltage and the current by the, if you guys want to know, if I have an ammeter, and I go to my panel and I heard 1000 amp, okay, that's easy. Slam on a meter, got you about 1000 amp. And the voltmeter, and I got my voltmeter to read a 480, okay, and this is a three-phase system. So I can do my math and take 1000, multiply it by 480, and multiply by 1.73 because it's three-phase component. And this amount here, guys, would be, this is the power volt amp. This is not the watt. The only thing that's missing out of this is the power factor. This is missing the power factor. What is the power factor, Chad? I have no idea. What is the power factor? So what, guys, yes, you measure the power, but this is not the what we call it the true power, Byron. This is what we call it the apparent power. Now talking about different type of power. The apparent power, there is also the true power. The true is measured in watts. The power is measured in volt amp. Reactive, there's also a concept called reactive power. I don't want to confuse too much with this measured in VARs. And you guys probably heard about VARs for converters and so forth. Anyway, so moving on, there are three powers, and you guys will study this in details as you move through your apprenticeship, and I'm sure you study, some of you did that. But the particular meter is called watt meter. You will never hear Brenna people talk about volt amp meter. It's watt meter, measure the watt. So moving from these, and now moving into the more sophisticated equipment, we have now in the 4000 amp switch here, guys, we can specify, if you have a 4000 amp switch here, a lot of customers wants to know a lot of stuff about their switch gear. If you have an amp switch gear, you have a digital multi-function meter, guys, that you put right here in the switch gear. They give you a graph of metered value over a length of time. Detect spikes in the voltage, sudden drop in the voltage, the current, the power, record the voltage and the current. So basically, what we look at in major system, these are digital multimeter. They're not just, they can give you a lot of stuff. They can give current in every phase. They can give you the voltage to ground, the voltage to phase of every phase. They can get you the power. they get you the frequency, they can get you the power factor, they can get you if you have spikes in the voltage. If you get your voltage was going perfect, all of a sudden it went all the way up to the sky and came down. That pulled the spike in the voltage. That you that this spike. So then, Eric, my friend, you can go down to your plant and analyze it and see every time I start this chiller, it creates this resonant effect in business. So I might have to go solve this problem. So it gives you guys the signature of everything that goes into your plant. It's unreal. And I don't know, Jacob, if you guys have it where you work, but you can suck this information directly into your laptop. You can communicate with these meters. These are Ethernet enabled, and you can communicate with them, pull the information direct into your laptop as an operator, and in real time you can see what's going on in your plant. This 4,000 amps with you. So that means that is the sky. The limit, as I always say, is the sky in that one. Okay, about the watt meter. If I remind you of one thing, guys, about the watt meter, remember the watt meter you connect. It has two coils. One coil is for the current connected in series. One coil for the power connected in parallel. So what I mean, my friends, if you have a watt meter right in here, this is my major, let's say a watt meter here. You're gonna that for watt meters, guys. Here's my three-phase donuts. I three-phase donuts. Tie my three-phase donuts. Bring them. These are bring them to the to the meter, right? This is why I bring them. And also, guys, these are, I'm not showing it here. Now go to bigger system here. My phase A, here's my phase B, here's my phase C through these donuts. And I also, what I would do, I also have a voltage from here and another across the meter to sense the voltage. You might have to sense the voltage from two phases, multiple phases to give you to sense the voltage. So now you can sense the voltage. That's real for a meter, digital meter. I brought voltage and I brought current to it. Now this watt meter can read 10,000 watts, and so that's basically how we do an analog, a digital power meter, digital power meter in this day and age. Okay. Let's bridge circuits, guys. Now we're switching tracks here. Measure value of resistance, inductance, coil. You can, what you can do is you can put a bridge circuit, guys, to resistance and inductance or capacitance. You put a bridge, and if the voltage across these bridges are equal, then this resistor value is equal to this resistor. So struck by connecting 4 like components to form a parallel series circuit, 4 for capacitors, and this is a with bridge. I think we have a picture of that baby without getting too much into it, and and this is good, guys, to measure certain equipment in page in my book 300. 300 basically. So you have galvanometer, and you can have on R2 and RV and RX. You can start adjusting RV until you get the value of RX. So basically you put the resistors in parallel series and you put them together to find a value of another. I can't emphasize it could be a resistor, an inductor, or a capacitor. So one is the one, guys, of measuring Wheatstone bridge. It's in page 1. A picture of that one. You can adjust, guys, the existing resistors. You get 0 voltage, point B and D. Then by doing that, then find the RX from the math, associated with it. of the series must equal to the applied voltage. Anyway, using the voltage parallel series circuit, you can do that. 305. Thank you, Byron. SH305 in your book, guys. So, is accurate measurement of resistance and operates on the principle that the sum of the voltage drops in a series circuit must equal the applied voltage. In a circuit, must equal the applied voltage. When the points B and D reach 0, this means the resistance are, you can find the value of R resistance. We'll get into the math of that. That's what I have, guys, for you. Any questions, any comments, guys, about meters? If we summarize, guys, really real stuff is, I can't emphasize about investing in a good clamp-on ammeter. It could make your life really easy. Good clamp-on ammeter. 1 amp is good, always good. And also a good voltmeter, guys, that can read the volts for you, line to ground, line to line, and so forth. With, guys, comes a lot of measurements. You have continuity measurements. You can check continuity. You can check the resistance of the coil. You can check diodes, capacitors here. There's a lot of things that you can measure from these multimeters. But that's the importance of investing on one or a few of them. Okay, I'm going to go, guys, and give you that little poll for the night. Before we move on, I have 60 in this option, and let's give you let's give you close to 7 minutes. Let's give you a minute, my friends, and you guys can chew on these questions on 21.6. Directly to the meters. Okay, my friend, I opened it for you guys. I'm looking at it. I thought it just changed. Okay, now you guys have it. Sorry. I'm glad, Jesse, that you're awake, bud. All right. Okay, let me go share the results. Correct. And so, any questions about the poll? Any comments? Any questions? Any concerns? Any questions about the poll? Can you guys hear me? Anybody question about the polls? No. So, with my friend, that will basically wrap our a few exercises I want to mention. There is in page 21.8, guys, really good exercises if you have a lab. We don't have a lab, would be really interesting to do the oscilloscope measurement and volt VOM measurement with volt only and meters. So a few things if you guys have a chance and be in a list to do exercise. If you don't have a chance to wire them, at least read them in a study guide. Just read them. Related to a DC power source, powering it, adding a couple of resistors, and taking, here's the voltmeter. Studied how the voltmeter, guys, I can't decide, look how it's connected in parallel. This should be second nature for electricians. And if you have a meter like this, it's in series. Alternative for a series meters, as we all know, with the clamp on ammeter, ammeter. So either it's going to be in series or a clamp on ammeter. And ask you guys to find the current here, find the voltage across A and B, and so forth. Same thing for this lamp. I can't tell you guys, it's really nice to understand. Let's say if these two lamps are the same, just by looking at them, say these two lamps are the same, you close S2. Hopefully, I hope that each one of you guys can tell that each one of them will have 4.5 volts. I hope if same, and if the voltage across this one will be also 4.5. So these are things that are really nice to know about this. Guys got from the DC, since this is last for the DC. Just FYI, always the smallest slot is hot. The longer one is the neutral, and the little smiley face down at the bottom is the ground. So these are jobs, guys, that you do. Summarize, my friends. If you don't have any questions, this will wrap, Brenna, friend, the DC part of this year. So next week, my friend, what I'm going to be doing is I'm going to go switch directly into the DC code book, and we're going to move away from the DC and the series and the parallel circuits, and we start talking about the AC, the DC, and in particular the wires. I'm going to walk you next week, guys. I'm going to teach you everything you need to know about how to size a wire for a 4,000 amp switch gear, 200 amp panel, load sensor, and so forth, and do a voltage drop calculation at the same time. So that will be next week. I remind you guys that next week is also a block exam. We're going to have 40 questions block exam next week. So week is NEC wires block exam, and 3 more classes to go. I know you guys are probably tired of hearing Chad. All these we started in September. Has been a long ride. So just 3 more. I'm sure excited to get done with the whole apprenticeship training here. So 3 more. Remember, we're going to do wires next week, and we have a block exam. One more time about the homework, please drop me an email. If you want me to email all the homework, please email me the homework so I can give you credit for it. And what I'm going to say about the homework, just drop me an email at seekerly@dunwoody.eu, and I should be able to respond to you. And I think I emailed it to somebody. So, okay. Or the next chapter. The block exam will be up to the next chapter, Byron, my friend. So next chapter, the wiring will be included in the block exam. Yep. So now you can still having a quiz, you will have a block exam. before we wrap up, Matthew, Joe, Joanne, any questions, my friends? Questions? Thank you. Questions? Question. Thank you so much for listening to Chad. I know it was a tough topic to talk about meters and all these DC and AC. You guys like the expressions. Keep the good work. Grab your meters and off we go. Okay, that's all tonight. If you have anything, just hang around. Otherwise, good night, and we'll see you next week.